or you just gonna, how are you gonna distribute the grading back to us?
Good question. Yeah. So I think so. First, we will give it to you, right? And we can either email you individually, or maybe there's some simpler method, right? So we can either email you, one by one, or we can, yeah, if there's some smarter idea, we can also try.
Yeah, like let's say on Blackboard, what professors usually do is that they have this turn-in method, and they can give us feedback right there, and we can see the grade and everything set up. So
okay, yeah. So
no,
we will, yeah. So we will certainly give you feedback. Yeah, we certainly will give you feedback. Yeah.
All right.
Yeah. So yeah, we will give you feedback, and it's like the actual like a homework grading and the physical homework grading, and you can see it. And also we will have like a midterm review session. So we will get you prepared for the homework and give you feedback. Okay. Yeah. So if there's no more question, let's get started for today's lecture. So we will talk today. We will talk about kind of like two topics. One is the kind of like PID control implementation, in particular about how you implement in the microcontroller. And we will also talk about the motor control, something like the Mechatronics, right? So the right one is kind of like Mechatronics, kind of like the hardware configuration. The left one is kind of like a software implementation in embedded system. So that's what we will cover today. So I think this is kind of like a very interesting topics that you can help you to learn some very practical aspects in mechatronics. So let's go back to our kind of like a syllabus. As you know, we cover several sections. We already talked about the programming in the last few weeks. So we primarily focus on Arduino programming using C language, right? And the second section is about the actuators. So today we will talk about the PID control and the motor control, right? So this today's lecture, and it falls into this actuator, this category, and we will have you learn about the mechatronics and the control or like a mechatronic system, in particular about the actuator, electrical motor, this kind of like actuator. In the next few weeks, we not only will have midterm, right? So we will have midterm, but we will also do some like a midterm review to help you prepare the midterm exam. And the third section is about sensors, right? So the sixth section is about sensors, and we'll talk about force sensor, inertial measurement unit, this kind of like position sensor. The last portion, we'll talk about the control and how you can use control to put all those components together, right? From programming, actuator and sensor all together, and to control a robotic system. So all you can also think about this kind of like a robot system and integration of robotic system. If you look at the vertical lines, and you can realize that we have this kind of like a lecture, right? The vertical is a lecture. We also have some like underlying theory. And because this project-based experiential learning, we also have this like lab session and project session, and in particular about the final project, right? So I think this will really help you to kind of like really get prepared, how to really get you prepared about like many different aspects of mechatronics. Okay. Yeah, we have one more student. Okay. The next slide. Yeah. The computer is kind of slow. Give me 1 minute about the. So Yeah. So today we will first give you some overview about some lab section. So it's just an overview, and you will see the details of this lab section in the lab after the lecture. And just want to give you a general overview and also make you kind of like refresh your memory about the motor control and prepare for your lab. And we also will talk about this final project overview and talk about today's main topic is the PID control and motor control. This is for today's lecture, and so this is the main topic for today's lecture. Yeah. So in terms of lab overview, is we kind of like talk about the PWM control in the last lecture, and we talk about how you can control the motor through the duty cycle regulation, this so-called PMW motor speed control. And we also talk about this kind of like control, kind of like a hardware, motor driver. Do you, anyone still remember the name of this kind of like circuit? Do you remember what this
H-bridge?
H-bridge, right? Great, yeah, H-bridge. Right? So H-bridge can be used to control. Can you say a few words like what H-bridge can do? Do you remember?
It can control the direction of the rotation if you're going forward or backwards.
Yeah, very good. Yeah, right. So in this way, and you can see it's rotating clockwise, and we can, if we use the microcontroller to control the kind of like the gates of this H-bridge, we can also switch to like a counterclockwise control rotation, right? So as you know, like through the microcontroller, it can regulate both the kind of like the direction pin and also the motor duty cycle pin. If you control those two pins, and you can essentially change different pins, like what pins you will control, and also the motor speed. Because for example, the duty cycle is proportional to the motor speed, right? So if you give like this 25% duty cycle, it's basically regulates motor speed to 25%, right? So they are kind of like essentially equivalent, right? And we have developed this like kind of like a CUNY Mechatronics kit, and it's a kind of like a low cost like a Mechatronic kit system. And we have reduced its cost from about $300 to this one to about $100. And it's also very ideal to learn this closed loop control system. And I think, as I mentioned before, I really want you to learn this kind of like a system level concept, right? So it's not individual components, it's a robotic system. And in particular, this closed loop control system, right? And in terms of this DC motor control, and you can see we have this kind of like modular plug and play kits. Then you can kind of like connect the pins through this connect the pins through this like a kind of like a quick connectors. So it's a very reliable, much more reliable than the default Arduino system. So yeah, we will use a little bit of this kits in combination with the kits that you already get at home, right? So in particular about the motor control, we have this, let's see, we have this motor driver. You can see this this one is the motor driver, right? So this is our motor driver, and also this is a motor driver. Also, you can see we have this. You need to connect the different pins to enable this kind of like a different PWM and the direction control, right? So you need to configure your system to enable this kind of different functionality. Okay. So very brief overview. Any question?
Yeah. Do you have any diagrams that can represent the motor board?
Yeah, we will show you the diagram, right? So the most important one is, I think, first you need to know this called it's called a shield. So it's called a motor driver shield. It's one type of shield that basically it's kind of like it's kind of break out the pins from this kind of like motor driver. It's called a L298 driver board. And it's a dual motor controller, means it can control two motors, right? And from this diagram, you can see, right? So on the left, you can see this is a kind of like a H bridge, and this is the second H bridge, so it can control two motors, right? And as you asked about the different pins, right? So this is the pin diagram for this motor driver. And you can also find this kind of like the detailed pins from this diagram, right? So for the Arduino Uno, and you can see the pins configuration, and from this side, and this is kind of like the hardware pin, right? And you also need to write the Arduino coding, and so including the pin mode configuration, if you want to control it as the input pin or output pin, right? And then you also have digital pin and digital output pin and analog output, right? So you need to configure different options. And for the PWM value for the Arduino Uno, it goes from 0 to 255. It's corresponding to this kind of like a motor spinning like a speed from stop to full speed rotation, right? So I will briefly go over the code with you because this is just an overview for the lab. And you can see the, in the lab session, we will go over the detailed coding. So just to give you a brief overview, right? So you need to, as we mentioned, you need to configure the pin mode, right? For the PWM pin and also directional pin. And also you need to initialize the pin outputs, right? So this is kind of like the first step, right? Kind of like the setup, right? And we also need to define some motor faction, and this is kind of like a custom motor faction. We define that it has the input including the direction, the rotation speed, and which motor, essentially which pin you want to control it, right? Because for this, you remember this like a H bridge, chip, right? And also called Arduino shield, right? And it can control two motors, right? So you need to specify which motor you want to control, right? And then we also remember this kind of like the different values corresponding to different speed, right? So you need to use analog to write this faction to specify the speed, right? So this speed is this speed, right? And the different value will regulate the motor to rotate at different speeds. And of course, the third step is kind of like you have this main loop, right? For the main loop, it will continuously operating, and you can define different like implement different functionality by calling different like this faction. We already defined this faction. You want to specify which motor, direction, and the speed, right? So you can like configure different motor like a faction in this main loop, right? So this is just a brief overview. So let's look at the final project. And for this final project is some like really you need to almost start from scratch. We provided this components, including the motors, the sensors, and this kind of like the basic mechanical components. But you need to do your own work because this individual final project, and you need to do the mechanical design of the elbow exoskeleton, right? You can learn about mechanical design, and also you will apply what we will teach you about the sensors and actuators, right? So because we will cover about different like electrical motor, servo motor, right? And also we'll cover different like a load cell sensor and MU sensor, right? And in the end, you need to, the third aspect is you will learn how to do this MU-based intention detection, like do the programming to implement your controller, right? So just a little bit detailed information includes you need to design and assemble your elbow exoskeleton, and you need to 3D print it. So we can help you to print some, right? So, but you need to do the design. And also in terms of the controller, you'll learn about the position control, force control, and also this is called admittance control. So really quite a few control options. It's really a very nice platform. It's like a new product that you can learn various aspects of mechatronics. So a simple like a video to show, we already made this kind of like a version, so we want to make sure it works. So in the end, you make your own version based on your personal dimension. So some students will make it bigger, some students will make it smaller, right? So let's start today's major like a lecture topic about motor control and PID control. And I think you already learned this in the last two lectures about the mechatronic components, right? So we have this motor driver. We talked about this the H-bridge driver circuit. I think it's called L298. This kind of like a motor shield that can be attached on top of this Arduino motor Arduino system, and you will use that to control brush the motor. And in the end, through the product, you will use the motor to drive exoskeleton, right? So this is called the block, right? And we close the loop through this position sensor, and this encoder is a position sensor, right? So through this position sensor, you can calculate this tracking error. Before we talk about the PID control, we want to understand in the last lecture, right? So we talk about the modeling, right? We talk about why we need modeling of this like a motor system, right? And we also talked about for each motor, it has two major components, right? Two aspects. Can some student think about this about what? This is one kind of like aspect of this motor. This is another, the second aspect of this motor. So it has two aspects of model.
Mechanical and electrical.
Yeah, can you say that again?
A mechanical and electrical component.
Right, this is electrical, this is mechanical, right? So if you look at this kind of like the motor model, right? So this is corresponding to the electrical model. This is corresponding to the mechanical model. And how are those two models are connected together? What's the link between those two models?
Current.
Yes, right? So because we know, very good, right? So we know the current will be proportional to the torque, right? So because the current is from the electrical model, right? And the torque is primarily about the mechanical model, right? So through this link, you can build the relationship between this electrical model and the mechanical model, right? And so overall, this motor model, right? And another related question is why do we need to learn the model of motors? Why? Why do we care about the model of a motor system?
It helps you decide if it's going to be beneficial for your application.
Yeah, that's one answer, right? So yeah, it's yeah. Another aspect is for us if we want to design some controller, right? So this is called if you want to design some controller, this is about a model based control, right? So if we have this model, right? So this we call this model, right? And for our controller, if we can model the system very well, we certainly want to have some kind of model of the system, so we can know precisely how to control it. So maybe we can compensate some parameters, some dynamics of this motor, right? This motor dynamics through this kind of a controller, right? So PID is one controller, right? So it could be any controller here, right? So for example, it could be a simple P controller, or could be a D controller, or for a PD controller, right? So there are different kinds of implementation of this kind of control algorithm. How to say you can do a different controller design. So that's really some kind of art that you need to you can learn in more advanced control classes. So today we will focus on this part about how we can implement, right? Maybe the most popular controller, the PID controller, in the Arduino system, right? So from this diagram, right, you can see the input, right? So the input is an error, right? The output is some kind of a control signal, right? So we want to define how to use this error to calculate this output control signal, right? So the we want to find some kind of a mapping from the error to this control command, right? So that's the goal for our controller, right? So if we look at this kind of generic model, and we talk about the plant, the actuator, the sensor, and this kind of motor driver. So this is about the hardware, right? So the overall system here, right? And we need to actually, we can define some a controller here, right? So the software controller to command the motor driver and to control the plant, right? So that's the kind of the goal for any controller. And we talk about that. Switch. So and we talk about we are trying to find design a controller so the output can track the desired input, right? So if you prescribe some desired input, and we want the output able to track it precisely, right? So so that's the kind of the objective of any control system, right? So if we have this control input, the error, and we calculate the output, right? So can you think about what a controller, right? So this is a controller, right? So can you think about what should we put inside the controller? So the U should be a fraction of error, right? So what should we tell the controller to do? So what kind of operation you want to do with respect to the error?
Implement some transfer function that can feed it back to the output.
Yeah.
Yeah, so the error.
Right. So we can do some a very simple operation, right? So the very very maybe the simplest controller is this called a P controller, proportional, right? And when we have error, the output, right? So you just do a KP and multiply by the error, right? So this will be your controller, right? So this is called a proportional controller, right? So the constant KP is just some a number that you can prescribe and set up, right? And in terms of E, right, the error is about the current error. So let me move this kind of this video a little bit so you can see the whole screen, right? So if you look at the diagram in the bottom, right? So if we think about this diagram, right? So the axis is kind of like the, sorry, let's go back. So if you look at the x-axis, is the time, right? And the vertical axis is error, right? So if you look at the current timing, right, the t, right? So we can divide the error in terms of previous error, current error, right, the present error, and the future error, or the future dynamic system, right? So if we think about this kind of the proportional controller, right? This E is just the ET, right? The current error, right? So this is kind of like a simplest controller that you can leverage to command the output, right? So can you think about why we also need to maybe use the kind of like this called I, right? The integral term and the D term. Conceptually, can you think about why we need the P term, right? We need I think the P term makes sense, right? Because we just give some gain to this error, right? Can you think about why we need this integral term and also derivative term? Any idea?
To calculate the future.
Right. So the D kind of like is kind of like this zone, right? D is like this zone, right? So this is like you want to have some prediction, right? Some prediction about what the system will go, the dynamic system will operate for the future term, right? Why we also want to care about the integral term?
It's the accumulation of the past.
Yeah. Okay, yeah. So that's because, right? So because we can understand what happened before, right? So if you remember kind of this kind of the history, right? If you remember, let me admit to one student. So if you remember the history, and you also have a history here, right? Remember the past and predict the future. So this is kind of like your future prediction, right? So that's the kind of like the high level definition, kind of like the philosophy why we need a PID controller, right? So that's why it's so popular, because it can consider the present and also remember the previous, remember the history, and also looking forward, right? So this is kind of like the crystal ball. Then the controller is smart, then it can consider all three time domains. Does that make sense?
Okay,
Yes.
please repeat
Yeah.
that.
Any question or comment?
Can you go over that again, please?
Okay. So yeah, so let me clean this. So when you have an error, right? So you have error term, right? So you want to have some operation, right? To calculate your output. The output U is a fraction of error, right? So you need to do some like operation, right? The simplest way is we just give some proportion, right? So let's say if the error is 0.1 radians, right? And if you want the robot to move to 1 radian, right? So if you want to move from 0 to 1, and currently the current position is 0.1 radians, right? So the error, right? So you can calculate the error is 0.9, right? So when you get the 0.9, this error, how do you want to use it, right? So you can do a simple term, right? Just multiply by a kind of like a constant number, right? Because the U is kind of like the voltage, right? It's kind of like, it's not the same thing, right? So it's kind of like the control voltage, right? and it will be amplified through the amplifier, right, to a bigger voltage, right? But essentially, this U tell the motor how much you need to drive the motor, right? So if we have this kind of like a small e, right? But if we want to drive a lot, right? You can give a bigger K, right? Bigger KP. So if you get error 0.9, you can give 100. So the U will be equal to 90, right? So 90 maybe it's 90 watts, right? So 90 some unit, right? So you will use 90 watts to drive a motor, which is a lot of voltage, right? So if you think 100 is too large, maybe you use like a 10, right? Then you get a 9 watts voltage output, right? So this is considered the present, right? However, as you know, like if you only look at the present, the drawback is you only know the current kind of like status, right? If you can also, so basically you can only utilize this moment, right? However, you already know this history, right? You already, for example, from this to this, let's say this is 100 second, right? 100 second. You already have like a data in the last 100 second, right? So if you only use P, you only use 1 point, right? If you use the history data, right? You can use all the 100 second data, right? So that's the kind of like the history term. And if you want to look at the future term, right? Based on the current slope, you can also predict the future, right? Very likely, maybe it'll go this way, right? So based on the slope, you can also predict the future, right? Is this clear to you now?
Thank you. Yeah.
Okay, so that's why, right? So I think this is a general philosophy, right? And in terms of detailed implementation, if you look at this, right? So this is the detailed implementation. We talk about the KP, right? The proportional controller, right? So if we want to look at the history, how do you calculate the history of the error history? How do you calculate the error history?
You can integrate the error between the time you want to figure it out.
Yeah, you can add up the numbers, right? So you can let's see if you can, for example, this is the error, this is another error, right? There's another error, right? So you can add all the errors together. If we call this EK, right? EK, because in microcontroller is a discrete system, and if you define this as EK, and this is EK, right? And you also know EK minus 1, right? And so this is EK minus 1, right? And you can go one step further, EK minus 2, right? So you know all the history data, right? So if you are in a continuous domain, and you can do the time domain integration, right? And this is the output, right? E is the error. You can integrate the error in the past maybe t, right? From 0 to t, right? And to calculate the kind of like the prediction, and you can calculate this term. So it's dE divided by dt, and you multiply by gain. So the question is, what does this mean? What's dE by dt? Is what?
The rate of error?
Yeah, rate of error. Do you have another term to define it? It is what? Rate is okay. Yeah, it's not bad. Yeah. Any other term?
The gradient.
Okay, gradient. Perfect. Right? The gradient.
Yeah, you want to minimize the error. That's why you take the gradient.
So yeah, also you can call it a slope, right? So the slope of this curve, right? Right. So because if you know the slope, you generally know like this is kind of like the future, right? But you know this is also not perfect, right? In this case, if the dynamics change, right? So if you do the slope here, you know it's continue doing this way, right? And so this is also you know first a PID controller is not perfect, right? But it's the most popular controller, right? For example, if the system, if the system is here, right? So if you calculate the slope, if the t is here, right? So you know the next step is here, right? So you can get precisely, I mean, some very good estimation about the next step. But sometimes if the system goes down, right? The slope will also change, right? So you also need to update your new slope, right? So the new kind of like a derivative term, right? So yeah, so that's the general idea, right? So if you look at this again, this is what? Remember this is what? Those three terms.
The
This is about
Present.
what?
Present.
Present, right? Present. This is about what? This integration is what?
Past. Yeah.
Past or history, right? So this is
And
about
future.
future, right? Have you learned about this before? I think many of you learned PID, but did someone teach you? But did anyone teach you in this way?
No.
No, yeah.
What do you
You
think
just
about this
taught
way?
the formula.
Right. I think you know, if I just tell you the formula, you know how to do it, but you don't know why you need to do this, right?
Yeah, that's true.
Right. So I think it's very important to know something why. It's not only know it. I think one thing I want to teach you is you know, to think about why, right? Not only how, right? I think learning how to do it is good, right? But learning why to do it is more important, right?
Yeah.
Yeah. So we have this kind of like a nice diagram, and if we change this, so this is the kind of like a time domain, right? So if we convert this to S domain, so what's the expression? Kp times what? So if we do the Laplacian transformation, right, to the left, to the right, so what do you get? This is equal to what? US is equal to what?
Times S.
Kp times what? In the Laplacian domain.
Times S, right?
This is Kp times error, right? So what was the Laplacian transformation of this fraction? Kp times what? Anyone else? So what's the S transformation of the KPE, KPET? It's simple, right? So how do you remember what's this? For the constant, we know after the transformation, the constant doesn't change, right? So it's still linear relationship, right? So what's the ET? Laplacian is what?
Isn't it 1 over us square?
No, it's just ES, right? Okay.
All right.
So what about the Laplacian transformation to this? To the second term, what's the Laplacian? So we know the Laplacian transformation for this is ES, right? Kp multiplied by T, yes. What about the second term? Ki multiplied by what?
S.
S what? Maybe the third term is easier. Do you still remember Kd And what's the S domain or DE dt? What's this? Wow, you all forget.
I want to say 1 over S.
S, yeah.
I'm talking about the derivative. Is it 1 over S or S? Which is
the function minus the initial value of the original function, the Laplace function minus the original value of the initial.
right? So you remember the final format for this?
Yeah, it will be F or whatever term you want, T S minus E to the 0. E at the initial position 0.
So we assume the initial is 0, right? So what's
Okay,
what's the yeah, what's the S domain of this?
then is this I'll call it a function of S then. And
Yeah. So what's the expression?
Isn't it gonna be
it's gonna be E of S in this case if you writing it like that.
isn't it gonna be what S E of S minus E of 0?
Yeah, let's assume 0 is 0, right? Initial
Yeah.
condition is 0. So is S multiplied by E or 1 divided by S?
No, it's
No,
S
it's gonna
multiplied by
multiply.
E.
S times
Multiply.
E.
Yeah.
Right.
Yeah.
S times E, right? S times E, right? So this term is S times E, right?
And
Because
then plus the original.
yeah, derivative is just S in Laplacian domain, right? What about this term for the integral?
Integral is gonna be the division of
E,
it's gonna be
yeah.
E over,
E over
S.
S.
E over S, right?
Yeah.
So because we have E in every term, we can take it out, right? So it will become Kp plus what? Ki
Over S.
over S, right? And Kd, right? So this is the operation with respect to ES, and the US is equal to this, right? So this is the Laplacian domain, the PID controller, right? So this is a L domain controller, right? As expressed here, right? So PID controller, and you have the option to change all 3 terms, right? So those are constant, but you need to pick up those constants, right? So you need to figure out how to do it, right? So for example, so each term, the Kp, Ki, and Kd, they have different functionality, right? So let's look at what it can help us, right? So let's use this example, right? So let's start from P controller, right? Just the simplest controller, the P controller. And we wanted to, let's say we have like a position, right? If the motor position, initial position is 0, right? So we want to go to 1, this position 1, from 0 to 1, right? Let's say 1 radian. This is the position tracking problem, right? So if we just give a Kp, if we say Kp is 30, another Kp is 300. And if you put this in this Simulink model, you give this reference position, right? From 0 to 1, right? So this is your reference, right? And you do this error calculation, and the simplest Kp, right? You can calculate the Kp term, right? Sorry, you know the Kp term, right? And you need to tell what the Kp term should be. Then you get a number, right? So this is, so the input is E. After this Kp, what's here? Do you know what's here? What's the signal here? If you read the signal here, what would the signal be? So this term is called E, right? What's this?
Output?
We call this KP, right?
Oh, it's EKP.
Right. So KP multiplied by E, right?
E. Yeah.
Because in Simulink, this means kind of like an amplifier, right? It amplifies the E, right? So you get this number, right? KP multiplied by E, then you feed it to this motor, right? So you get like an output. So if we do this simulation, you will see that, so if you give a bigger KP, because of this output is larger, so it will increase dramatically, right? To a very large number, right? So increase, but because it's too fast, it also needs to go back and back and forth. So kind of like the motor rotates this way and this way, so back and forth. But for a smaller KP, right? It goes up and kind of like stays here, right? So what's the problem of this? Let's say, what the problem is of this controller? This KP is equal to 30. We want to go to 1, right? So what's the problem with the KP controller? KP equal to 30.
I think the voltage is going to be very low.
So from this diagram, can you see the problem of this controller, this blue controller?
It's about half of what we originally wanted.
Right, we wanted to go reach 1, right? So we want to reach 1, but it can only, so it has this steady state error. It's not good, right? So it cannot reach the number. What's the problem with this larger again? What's the problem with this?
The error is too large.
Yeah, and because this is the problem, right? So this is called overshooting, right? If you still remember from 411, right?
Yes.
So, you know, if it's too small, it cannot reach a number. If it's too large, it overshoots, right? So, you know, it's tricky, right? So the large P gain will cause like a large oscillation and large overshooting, right? And a small P gain will lead to a large steady state error, right? Both are not good, right? So, but from this diagram, we can make some like initial conclusion about the KP, what a KP can do, right? So from this you can see the KP can help you to kind of like you see, if the KP is too large, in this case, it can cause overshooting, right? And if you make the KP larger, you can decrease the steady state error, right? So this is good, this is bad, right? So if your KP is large, right? So assuming the KP is larger KP can reduce the steady state error, right? You see this here, you see the larger KP have the smaller steady state error, right? So this is good, right? But in terms of overshooting, larger KP, let's assume we have larger KP, it has a bigger overshooting, right? So that's not perfect, right? So one solution to make this better is we add the I term, integral term, right? So, you know, the output here is kappa, KP minus, multiplied by KE, right? So what about this one? What's the output here? What's the output from this this pin? It's KI something, right?
Yeah, KI over S.
KIE over S, right? So if we add them together, you add this term with this term, right? You add them together, you get a KP plus KI divided by S and E term, right? So this is what you get like from this PI controller, right? And if you look at the result from this PI controller, and you can see, right? So if both they add this kind of like a PI controller, and you see this, if you add like a if you use the same P gain, it gives different I gain, right? So you can see, you see both will have better performance, right? So you see the blue line, right? The steady state error is getting smaller, right? And which is good, right? And in terms of this, the bigger, this is like this KP, right? And if we had a bigger KI, and we get rid of the big overshooting, right? It still has some overshooting, right? It's not perfect, but better than this case, right? So yeah, so this is the kind of like the capability of the KI controller, right? So if you increase the KI, and it will reduce. I think we cannot say eliminate, right? We can say reduce the steady state error. But if the KI is large, right? In this case, right? In this case, right? In the orange line, if the KI is large, you can actually increase this overshooting, right? So in comparison with this blue line, right? Because the orange line has a larger KI, so this like a KI is equal to 100. This KI is equal to 30, right? So like you see, the KI is useful, but it also increases the overshooting, right? So we can see now overshooting is a bigger problem with the PI controller, right? And also the P controller. So one solution to reduce the overshooting is we add a D term, right? Here we add the derivative term, and from the original controller on the left, if you add both KD, you see the orange line have a really nice tracking performance, right? And so we get a smaller overshooting, right? And we also like you see, it's a pretty fast response, no overshooting, right? I mean, there's a little bit of overshooting, right? Very little overshooting, right? But the problem, but there's only one problem with this KP controller. What's the problem? Can you see?
It's a little below what we wanted still.
Exactly, right? So if this is our desired position, it's a little bit below what we want, right? So remember, from the PI controller, we can reduce the steady state error. This is really, really useful, right? If we only use the PD controller, you still get some kind of like, you know, this, it doesn't improve the steady state error, right? So if you want to get all the benefits, you can consider put all three terms together, right? So this depends on the system characteristics, right? So that's why PID is so popular, right? So if you look at this combination, and we have zero overshooting and also perfect tracking, right? The steady state error is looks like almost zero, right? So that's why the PID controller is so useful. And so besides the overshooting and the steady state error, those three terms also have effects on rising time, settling time, and the stability, right? And so that's the general idea about the PID controller. So so this is like a time domain, right? Continuous domain. So how can we do this in the Arduino system? How we do it in Arduino system? So what's the difference between? So can we just do this in Arduino? Does this work?
You can use Simulink, and Simulink can connect to the Arduino.
Okay, that's one solution, right? And if we think about Arduino itself, how can we do everything in Arduino? So let's say you want to do the PID controller inside Arduino. So what's the? So this is like a time domain, right? Continuous time domain, right? So what's the big difference between you know, this is kind of like an ideal mass model, right? But if you need to implement it in the hardware, so what's the major difference? Do you realize the difference?
Wouldn't you have to create some sort of flowchart or pseudocode in order to implement this closed loop system?
Okay. Any other answers? So this is a continuous domain, right? So what's the difference between this mass and Arduino system? So we actually talk about this. What's the difference? What's the major difference? We actually talk about this many times. So your computer or Arduino, what's the unique about it?
You said a computer and Arduino?
Right, or Arduino. What's unique about Arduino?
It's smaller.
Yeah. What was the? I talk about this continuous time domain, right? In the mass, right? So if you really want to implement it,
Does it have to do with alternating a DC current?
that's not the major difference. So Arduino system is what system? Arduino is what?
It's a microcontroller.
Microcontroller. Can you get this? Let's see if you get it. You have the time domain, right? If you this has the error, right? You see this diagram, the time, right? Can you get a continuous timing?
Yeah, you can read the values of such.
You can read it, but the timing is what? Is that a continuous?
No, the timing is discrete. You gotta take a certain amount of value.
Exactly. So that's the difference, right? So Arduino system is a discrete system, right? So you cannot just you know, plug in this equation and it will work, right? Because the Arduino system, as we said, is discrete system, right? In the Arduino system, because it's discrete system, you cannot just do this one. It doesn't work in the Arduino system, right? It works in the mass. So you need to have the discrete format of the PID controller, right? So I will just briefly go over this. We can keep talking about this. I think I will show you.
Professor, by discrete, do you mean it's an intermediate process or
No.
What do you mean by discrete?
So discrete means if you look at this error, right? So let's put a simple way, right? If this is time, right? And if you want to measure the voltage, right? If you want to measure the voltage, right? And from the Arduino system, if you want to measure the voltage, the output, right? You can not measure the voltage continuously. It's always like this kind of continuous because it's digital system.
Right, because you get an intermediate output. Like you don't always get a continuous output. Like you get a bandwidth, like your band rate is a certain certain amount of data come back to you. Like for example, when you're reading something off a serial monitor, it's like, you know, it's not continuous. It's just intermediate. Correct? Is that what it is?
I'm not sure if intermediate is the best way to talk about this, right? So it's something like this, right? You have this quantization, right? So because you cannot read like an infinite number, right? So you cannot get this you cannot get the actual t. You can get a tk, right? Does that make sense? Yeah. So in reality, you can never get a t. You can only get a tk, right?
Right.
So the k is the timestamp, right? You can get maybe say like 3 p.m. You can get this. But if I want you to tell me 3.0001 p.m., you cannot get it because you know, it's a discrete system, right?
I see.
So yeah, it's not continuous. That's the major difference, right? So because this, we cannot simply do this way, right? So this, you know, the equation works in math, right? But this equation doesn't work here, right? So for example, to get the error, right? So you need to, for example, you need to get the reference position and the actual position, right? You get the error, right? You calculate the error. So, you know, R minus P, right? So you get this error with respect to this moment, K, right? And to do the U, you also need to calculate, for example, the UK is current error, right? This term is what? This term is what? What's the second term here?
Past.
Yes, it's possible. Is what?
Times.
It's a summation of the error.
Yeah, this is summation of the error, and this is a discrete domain of this integration, right? Because in discrete domain, you cannot do this integration in this way, right? Doesn't work. You need to sum them together. Similarly, for this term, you need to do the dE, right? So this is the dE, this is a dt, right? So dt is equal to t, right? So you need to calculate this term and so calculate all the three terms in a discrete manner, right? So for example, give you some like a kind of like example. So let's look at the P gain, right? So if you look at the P controller, right? So the controller it just have a P, and this is a kind of like our kind of like a plant, right? So the plant, the controller is just a P, right? And the red is the next value, and the black is the current value, right? So if we look at this P controller, and let's look at how this discrete system works. Initially, everything is 0, right? And this is a plant, this is our simple controller. If we want the robot to go from 0 to 100, right? From 0 to 100. And the reference is equal to 100, right? And the previous error, sorry, the previous measurement is still 0. And we can get this error as 100, right? So in the beginning here, the position is 0, right? The current position is still 0, right? So if you look at the position here, right? Yeah, so the error is 100, right? For position here, right? So initially it's 0, right? And this error, if we multiply by the P gain, we get the controller, right? This is your U, right? Your U will drive this system, the 50 will drive this to the output will be also be 50, right? Because this is a discrete time, right? So the K, right? The K, let's say the K is equal to 1, right? So if we go to the next step, right? So K is equal to 2, right? And it's kind of like a 2t, right? So you see here, so this is the kind of like the current value will propagate to the update this this output will update this kind of like a previous value, right? To 50, right? So you get a new 50, right? So the system from 0 goes to 50, right? And you get this kind of like a propagation, like what we did the last step, and the output will go to 75, right? From the first step is 0, for k is equal to 2. For example, k equal to 0, this is 0, right? If k equal to 1, right? So this is 50. So in this slide, we can go to k equal to 2, right? So the output will be 75, right? So similarly, if you go up and up, right? So you see the tendency is like when it go up, it's kind of like slowly going this way, right? It's slowly going this way. So the slope is getting smaller and smaller with this PID, right, controller, right? So ultimately, you know, we can get something close to 99, kind of like close to the 100, this desired value, right? So if you go back to the detailed implementation, right? So if we want to do the PID controller, it's pretty simple. We calculate the error, and we have the reference count from here, right? So the reference count. And the encoder, right, can tell you the PK, right? So the encoder count, right? So you calculate the difference, you get the error. And if you multiply by KP, you get the PID output, right? Because this is just a simple PID controller. Any question?
Is this typically used for how typically motors start up, like amps?
Yeah, and I think many devices, even microcontroller, microwave machine, or many machines, they use a PID controller. And almost many things you can imagine, from some temperature controller to like a motor controller, PID is almost everywhere, right? So that's why I think it's very, very useful. So another controller, and we know it's the I controller, right? So we need to implement this, right? This is a summation of the errors, right? So we know how to do the error, and then we calculate the sum of the error. It's the sum of the error is kind of like the error, right? You get from the last step, you add up the current error, right? You get the updated sum of the error, right? And it will update the previous error with the current error, right? So because in this step we don't really use so this is your output, right? So we didn't really use this step, right? So the previous order, this update. However, if we want to calculate this, right? We want to calculate the EK minus EK minus 1, right? So that's why we need this kind of like, we need to update this, right? Because we need this kind of like tell the previous error. So this previous error is this, right? And the error is this, right? So it's kind of like an interesting way, right? So yeah, so you need to do this, the UK is equal to this term, right? So this is your DE divided by the DT. In this case, DT is just the time constant. So it's called a fixed step, right? Because this is capital T, right? So if you want to do PI, it's kind of simple, right? You just add up the kind of like the P controller with the I controller, right? And similarly for PD, you add the P controller with the D controller. And so that's the kind of like the simple way to implement this, right? So actually PID tuning is very difficult actually. And you need to do trial and error. You need to try many times. So for example, my students, they do this kind of PID control tuning almost every day when they do the robot. And they need to tune it manually. And there's also some like automatic tuning methods. But yeah, it's also the scope of this class. But you can know that there's some like a manual tuning method and also some automatic tuning methods. So this is kind of like the detailed implementation, and the section 1 is kind of like this called the kind of like pre-definition. This is kind of like you cap the PID output, right? And also you have this controller, right? The control the PID, the actual kind of like when you calculate the PID, right? You convert it to some PMW values from 0 to 255, right? And you finally you output this number through this digital analog converter, right? So DA converter. This is the last step. Yeah.
Quick question. The output of 255, is that maximum voltage in a sense?
Not a voltage. So for the Arduino, it's from 0 to 5 volts, right? And 0 is corresponding to 0. 5 volts is corresponding to 55. Right?
So exactly. So it's a value of 5 of maximum voltage, which is 5 volts.
Right.
Okay.
So yeah. So you kind of like it's kind of like discretized through this kind of as you know, it's from 0 to 255. They are all integers.
So in the last lab, it was shown that 5 volts was 1032, a value of 1032, and you were supposed to figure out what, let's say, 3.3 volts would have been and what kind of value would be given. Is 255 like a default value?
Yeah, for each microcontroller, you need to check it, right? So it's not really default. It's default for each controller, but you need to check the number, right?
How do you do that?
You need to Google, like go to the microcontroller data sheet, and you check it. So yeah, if you, for example, if you tell you maybe in the PMW section, right? PWM section, right? It will tell you, right? So what's the number, the largest number to control it? Yeah. Gotcha.
All right.
Yeah. So let me kind of like rephrase this. So so the actual, you know, this portion, right? We calculate the PID, right? So this portion, we calculate the PID, right? So here you implement your PID controller, right? So as we mentioned, and if you have like this is your PID controller, right? So this is actually you do this inside the Arduino, right? Arduino, right? So Arduino, you get this number. For example, if you calculate 187, this is your output, right? And inside Arduino, it also has this kind of like a digital analog converter, right? So if you convert to something, because the maximum is 5, right? 5 volts, you divide by 255, you multiply by 187, right? So digital analog converter will tell you, okay, this will be your final output of this, you know, 5 volts divided by the 255. So this you get it from the data sheet, right? And then you multiply by 187. So this is the U, right? You get the U from the PID controller. Inside Arduino, you can implement this coding, and you can also, Arduino also includes this DAC, right? So in the end, you get an analog output, right? So that's why here, you see here, it has like an analog writing, right? So when you tell this number, and the analog writing will actually do this calculation and tell the pin, the analog pin, to output an analog number, right? Because we said inside Arduino, it's a discrete system. And if we want to go back to the physical world, in the physical world, it's an analog system, right? It's a continuous time. The time is infinite, right? It's not a discretized, right? So does that make sense?
Professor, can I add to the thing of I don't know who was the one talking about the 255 and the 1023. The 1023 is only for reading values of voltages. This is for outputting values of voltages.
Right. This is 255.
Yeah.
Is kind of like as we said, this is about PWM, right? PWM, right?
Yeah.
So, right. So discrete domain is from 0 to 255, and the kind of the corresponding is from 0 voltage to 5 watts, right? So this is kind of like and you know 5 watts is small signal, right? Small signal, right? Small signal, right? And I told you, right? So in the Arduino, you do this coding, right? You do the coding, and it's download to the microcontroller. Inside the microcontroller, it also has this DAC, digital to analog converter, and in the end, you get an analog output, right? You get this analog output, then you use this to drive your motor, right? Because if you only give a number, let's say we said 1787, right? Just a hypothetical number. You know, you cannot use it to control the motor because it's digital domain, right? So we needed to convert it to analog domain. So that's why we have this analog write, right? So, you know, this function, okay? So I will stop here, and so you can take some time to digest this lecture. It's I think I hope that is clear enough, right? And any question?